Sorry for the disturbance. We'll start again.
Yeah. So, welcome back for our discussion, which we have discussed so far how to make a BMS, how we can, once we have a model, some kind of battery technology we have seen how we can model the batteries, or how can you bring your real-time battery data to the MATLAB, and then we have seen the battery cell level. We have monitored various parameters like voltage, current, temperature, and then we have estimated some parameters like SOC, SOH, and SOF, and then we have seen different operating states of the battery using BMS, and then we have seen how we can uh, fault diagnosis or fault monitoring, all these things like which are functions of PMS we have seen so far. So now what we do is that we are based upon the different chemistries of the batteries, we are seeing the operating characteristics and then BMS. Then we try to use this battery and BMS to charge, to make an efficient charger to charge our battery or discharge, like with the grid connector system. Right, that is the objective of our afternoon session, like after the thesis. That's what we are going to discuss now, and also we'll see the same in the matter. Alright, we see that there are various type of charges like onboard and offboard, right? When we say charges for this lithium ion like we use generally in EVs, generally Li, lithium ion, LiFePO, right? So we have seen they are the best battery technologies which we have seen in previous session, right? And then we concluded that what are the requirements we have seen. Means we need to design chargers so efficiently based upon SOC. Means based upon the data which we received from DMS, we can utilize, we can send the data to charger to charge our battery or discharge our battery so effectively. That is what we are doing. And we try to integrate that with the grid. Okay, let me open the simulation, overall simulation, and then we'll come and we'll discuss the chargers. Right? Mm, mm, so let me go and then one charger. Like, right, so now like at the simulation one well, we have made a grid connected charger, and also even I incorporated the solar also. You can see the different charger. Alright, so now we can see how we can make nothing is up. Right, you can see that. So I'll discuss. We'll have some theoretical understanding and then we'll come back here and then we'll discuss this stuff on the that you know that it can and then yeah. Next part is that we have discussed the chargers. First part is the DMS and then chargers and grid integration. We are discussing it and yeah. So you see that here we have uh, yeah. So we have like plug-in hybrid electric vehicles, EVs, pure EVs, HEVs. Right? All of this we use something for batteries. How you can charge that once you made a BMS to the battery. So effectively, we will take the data from BMS to communication protocol, and then we take a decision how effectively we can charge the battery. Right. So charging like systems are like two types. Like one is that onboard or outboard. based upon the way you are placing the charger, like you are placing inside the vehicle or outside the vehicle. And also there is two types based upon the nature of system design, like conductive or inductive. So, alright, sometimes wireless provide. So, and also we have like unidirectional charging and bidirectional charging. What do you mean by unidirectional charging? Means it is only, it doesn't have the ability to pump the power from the battery. Only it will take power, it will not able to pump back to the grid. It will only use that energy stored in the battery to drive your motor, not driving back to the grid. But in case of biodiversity, it is like supporting all the different functionalities of charges. Nowadays we are coming like V2X, vehicle to everything. V2G, V2H, V2L, V2V, vehicle to vehicle, vehicle to home, vehicle to road, vehicle to buildings, like vehicle to everything. We say V2X. For that you want even your charger must be a bidirectional. Right. From the BMS, we will take that information of our SOC, and then we saw that where you wanted to operate operating characteristics based upon SOC against the voltage. We have seen that. And like and we have an SOC, we conclude that 20 to 90% range of SOC you need to charge, then you will get a better performance. That's what we have discussed. That's what we learned in the previous session. And then also we learned that based upon the SOC, we need to change the mode like constant voltage to constant current, constant voltage depending upon the SOC. That is also we have learned. So we will use the data from the battery chemistry and EMS information to design the efficient charger with efficient functionalities that can be explained through bidirectional charging technologies. Right? Anyway, so there is a various based upon the power levels. The charges have been categorized into different categories. We'll discuss that. These onboard chargers, when you design it, there is based upon there is several constraints you need to fulfill, like weight, space, and the cost. In case of onboard, it doesn't matter like weight and space. There is no constraints related to that. But yes, of course, the cost we should be able to optimize. That is the thing. Like we'll see that. There is a when you make a charger like because different manufacturers make different kind of chargers, so it is very difficult to use one manufacturer charger to another. So because different manufacturers use different kind of things. So what there is some organization like IEEE or SAE or IWC, they are making a standards. Right. So, like earlier days, we have different kind of. Let us take even taking mobiles. Like we have different kind of small pin charger, Type C charger, or something. Like that. Now we have Type C charger. Right? So, like micro USB, mini USB, something like that. We have different types of USB ports. We have like that. But nowadays, you see all the laptops are coming with Type C. Right? Because now the standardization. Like different organizations they are working on the standardization so that one port is able to do multiple functions like even the same port can be utilized to transfer the data or charge the battery or something like that. Uh, like that, so now these organizations are working on the standards and different code they are preparing it. So these are the organizations they are working on that we should be aware. Uh, uh, Accordingly, we should be able to design to meet these grid the codes which are set by these organizations. Uh, what are standards they can right? Uh, Things are like countries like India, we have a lot of barriers like lack of charging infrastructure and countries like India are very cost sensitive market. Right, our customers always like they look for the economical chargers or economic products, right? So we need to make some economical chargers and develop some kind of charging infrastructure, and only this will be and also, like when you are charging these batteries from the grid or something like that, so they because like the chargers inherently they are nothing but a power electronic devices. All these power devices are like non-linear, so they may draw some kind of harmonics that may affect the utility. Right? Then we get some kind of harmonics. So we need to take care how to handle that, and also we need to take care of unity power factor operation while charging the batteries. So that those are things you need to take when you are making your better battery and its associated charger and also like as I said that available power levels we have different chargers. Level 1, level 2, level 3. What is level 1? It is like onboard. Level is like onboard, but the power ratings are different. Don't get confused. Both are onboard. Like level 3 is like outboard. Right. So you see that in case of a level 1, it is like only for single phase. In level 2, it is like for both single phase or three phase. Here you see the power ratings starting from 4 to 19.2 kilowatt, like 17 amps to 80. Whereas in single phase on board, level 1 is up to 1.9 kilowatt, is up to 20 ampere, right? Typically, if you are charging at your home, some charger you are using to your vehicle that must be comes under the level 1 because we have maximum capability to draw from a single home should not exceed this. So, right? So, why because like you are we have a permission up to like 20 amperes, right? So, from a single point in case of residential customers. Right. So, at home, typically you will be able to get a maximum this much in case of the charge. And in case of US, it is like one, because they have a low voltage gate like 120 volts, and if it is 230 volts like European or India, so you get this. Right. But in Europe, actually, their homes also, they will get 400 volts meters. But in India, we have in our homes, always in some cases, we get people, but that is not residential customer anymore. Right? But in Europe, even residential homes, they will get a bigger supply. So in that case, sunboard level 2 can be at home also. Right. But in India, level 2 means we have this kind of level 2 charges at some kind of public outlets are some kind of a big apartments or some kind of a shopping malls or somewhere they are having the up to this much power rating we can install. And level 3 is a high, very high power rating, it is of course level 50, like so. Right. So based upon like we have different varieties of charger. So because if it is, we know that if it is a low power rating, a low current, it will take a huge time to charge. Right. If it is a high, very high power, it takes less time to charge. Right. So that is what we can say. So this based upon the technology like PHEs will be used by 2 kilowatt hour, EVs like 16 to 50 kilowatt hour. Don't get confused that it is high power but it is taking longer because it is related to this. It is related to that. Right? 1 to 4 hours is related to PHEs, like 2 to 4 hours is related to this much power rating. So that is how it is. Right? So alright, so now we whatever we design the charger that must be efficient, reliable, with good power density, and low cost, and low volume, and low weight. Alright. That is our requirements. Right. So at present, depending upon several things like components, converter topologies, control, or switching strategies, that decides the operation of your charge. Right. So we'll see that some of the topologies are going to charge our batteries. Maybe or maybe the same thing you are applying to microcontrollers. Right. Charger is charger, whether you are using batteries in EVs or microwaves. Only thing is that technology may vary. Lithium-ion batteries used in case of EVs, in case of microwaves, we use this capacity. Right, because they are economical and there is no space constraint in case of a microwave. But in EV, there is a lot of space constraint. Right? You will get good things in case of lithium. As we have discussed already about the battery technology, so that's done. Now we see that implemented to if you are making some kind of a charger, so you need to have different platforms apart from the power circuit. If you are implementing the control algorithm, so you need to implement to analog controller or microcontroller, also FPGAs, right? These optical control algorithms will be implemented through either analog way or digital way. In digital, we have microcontrollers or DSP, digital signal processors, or FPGAs, field programmable interface. Even nowadays, you are hearing D-space, Opalati, Blackwood, all these are again they are also designed to one of these microcontrollers that is because they are the base technologies. These D-space, Opalati, and all that is they are like comes in the cost of lakhs because there you don't need the coding skills. That's what I mean. So no, main Sunil sir. Method. Method. Okay. So yeah, sorry for this one. Sorry. So let me continue. So now actually we have discussed different technologies we should have aware, but all of this either BMS or charges. Right. So and these EV chargers must be able to give a good power factor and low distortion. Right. So means low THD and high power factor are our essential requirements. That those must be our high priority while you are selecting the topology. So there are already various standards they are set now, but they are still standardizing it to make some kind of universal standards or but different organizations they have already provided standards. IRB 1.47, SAE 12894, IEC 12032. So these are having set the limits and also US National Laboratory Code NEC 690. So they set some kind of standards for allowable harmonics into the grid and DC offset current index into the grid. Right. So we whatever we design there must comply these things. Right. And so modern EV like we typically these like very old style of charger earlier like these they different manufacturers to adopt this kind of a style or converter to design some kind of charger. But now we have some advanced technology. What they use is bad bridge at the front end, and then they use some kind of a boost converter. Like typically it employs the perfect correction. Right, so when you only use this bad bridge rectifier as DC, you will get it, but that is not one thing that is not controllable. And second thing is that it needs a lot of harmonics to it. But that's why they made this perfect correction and also the control the current will get a low TSV to meet these standards. This is a basic version, like and they have used here interleaved nature because these interleaving nature we have to increase the power handling capability, and then also one thing in the current sharing is there, and second thing the ripple component will be low when we are like interleaving. Right, but in the next slide we'll see that there is some advanced couple. This is the basic one which we have discussed. Like one is an HDC average output that will be given to the conventional boost. In that the problem is that there is a electromagnetic interference which is very high. So that is what that's why they have done some kind of a defined applications. In particular, they have proposed that in 42 and 43. They have developed this engineering concept to reduce the one is that charging current ripple and electrolytes, and also EMI is little bit down compared to the previous one. And further, like some kind of a multi-level converter couple they have adapted with size reduction, on that direction they have some multi-level done. And then this like suitable for level 3 charges because when we are doing a multi-level like power handling and all that we have to do right. So typically these things we adapt it for level 3 charges like where we need high power. Like when we are doing for high frequencies like then filter requirements will go down. So when we adapted like inherent canal boost to the centrally boost by paralleling the switching network. So we get what advantage we will get the ripple cancellations of the output will be done and stresses on the output capacity goes down and provide a heat management for the input bit rectifier, and these all things are there, and also the power limited power levels up to approximately 3.5 kilowatt. Right. So that's why what these are advantages compared to this conventional boost. Right. So, but what we do in the next, what they have done in the next research articles, they say that there is some kind of a bridge PFC for this also. They have. We'll see them next slide to overcome the drawbacks of the previous this is like multi-level. We say that there are different voltage levels. We can say. This is like single phase, unidirectional multi-level charger. So for low power, level 1 and level 2 charge. All that is like you see that there is a direct rectifier and then like 3 level setup is there here, and also it is having like perfect correction alignment. Right, so it is having more one more switch and one more capacitor compared to the conventional one. Because that what happens is that cost and control circuitry complexity increased. Because of this additional switch, we need to have additional gate driving and additional control. Right. So, what is the advantage? What is the good point of this? So this is like if you see that in conventional converter, whatever device we use here that has to block an entire DC, but here you can say that half of the voltage has to be blocked. Means voltage handling, voltage stresses on the device is goes down. That is the only advantage when they have proposed. Right? And because it is like multi-level style of operation in there, so it is better THC compared to the previous one, and the EMMS is good, and high power factor and frequency operation compared to the previous one. That are the advantage. Alright, so and this is like complete like in earlier we had this is like what you say this is like one is the multi-level and second one is that we have single stage. Like only in one stage we are able to do that AC to DC. Like earlier we have seen that there is a diagram which rectifier and then some kind of multi-level boost based topology. But here it is like indicator. All the things are like one stress. And this is like this is the booster vectors and this is like multi-level topology and we can achieve that. Okay. So when we go for this kind of a structure, so it is like although it is having more components and more cost, but it is very they can handle high voltage and high current. That is advantage of this. And because of the low switching stresses and small and slow vectors and capacitors, like small positive components when they are going for this material. That are the advantages, but these are the raw material cost and components. And, like here we see that bidirectional bridgeless topologies. There is no bridge. We are no longer using a bridge. Right. So in a single stage we are able to get our desired stuff. Right. So like with only the switches and the capacitor we are able to convert this. Right. So here is the bridgeless sample you can get bridgeless and here it is like three phase. So personally, like single phase operate and single phase operate and multi-phase. We are operating in PWM mode as well as we are getting a DC with the single phase. Based upon the amount of power and charging time, location, cost, equipment, and effect on the grid, we need to track the power ratings and the power topologies. Right. So and typically, what are the components are there in EVSE? EVSE means electric vehicle supply equipment, like EV charging cards, charge stands, and plugs, and then power outlets, and battery connectors, and protection. So, and we see that like what we need, important consideration in charging time, how much fast we can charge, how efficiently we distribute the losses inside the system, what extent we can uh, give the power, like it should be modular when we make some kind of a charging infrastructure, it should be so modular so that we can extend the power handling capabilities and it has to meet the policies. Regulatory procedures, all these things, so we need to take care. And we can, depending upon like different origin, different place, things are getting varied. Like when I was in Germany before joining this company, I worked for this four chargers manufacturer company called Coastal. We used to make chargers for four-wheelers, the Ford, Volkswagen, and Porsche, Bugatti. For them, they are the original equipment manufacturers of the chargers. What we used to do in recent version, we are there, the company, they are making universal charger. Like, see, like in India, we have a different charger. In US, it is different charger. In China, it is different style. Even outlets are different, and then things are different because the voltage rating, frequency rating will change. Like in US, they have 68, and in India, we have 68 and 50. Different bits, and different voltage, they have 120 and 240, we have. Yes. Like that, different, but they are making universe, whatever grid you may have. You may have they make a charger for three-phase grid, a single-phase grid, a DC, whatever grid you may have. That charger should charge the vehicle or the battery, whatever source you may have, three-phase, single-phase, or DC. That kind of intelligence adding, where intelligence can be added through our intelligent control techniques or these artificial intelligence techniques, we can employ them to give some kind of intelligence which we have discussed among. Then even now our focus is that this battery and then grid integration, BMS. So what I wanted to say that nowadays we are having a so intelligent chargers are coming. So whatever did now no longer location specific. So whatever wherever you are, the single charger can able to charge the batteries. That is how. But earlier days, yeah, of course, it is like a location specific, which can be designed accordingly. You need to design the charger, right? Because of the voltage, frequency, and everything connection and transmission standards are different. But now, when we make a universal chargers, it can operate from 85 to 270 volts. Whatever voltage you may have, it single charger can do that. Even whatever frequency of the grid you have, 50 Hz or 60 Hz, yes, it can do that. Even you have single phase or three phase or single phase, three phase, or in some countries we have a DC grids, and some countries like Norway they have a two phase grid also. Whatever grid it may have, it is sufficient. Our charging factors are so intelligent now they are able to charge the batteries. And also, even if it is a three phase, one of the lines gone, no worries. Charger is still able to charge. Power. Even two lines gone, no worries. The line and motor is sufficient to charge. Like that, very smart, intelligent kind of chargers are coming. There are going to come in 2025. That is the project timeline that time when I was working on the last project. Alright, so most of the EV owners they are expecting their to charge their batteries during the night time, like overnight. So if you are charging, if you are using some kind of or EV, if you are using for a personal purpose, like in the night time, whenever you are going to rest, so you wanted to charge it. So based upon that, you need to select how much time you have, sufficient time you have to charge your vehicle, how much time you wanted to run your vehicle once it is completely charged, based upon all these things you need to select things, right? So anyway, if you are at home, means you are a residential customer, you have level 1 only. In level 1, there is varieties of power ratings like up to 20 ampere, maybe 10 ampere charger, 20 ampere charger. It is depending upon how much time you want to charge. Level 2, this is level 1, is the slowest method. Level 2 is like better than level 1, and their prices also range outside up to like 10 little price. Like, it is like that is for years. Like Tesla, they are giving very high speed chargers. They are going almost fast compared. And the different standards on the connectors we have different uh, communication protocols because why we need to do that is that I just said that the chargers are nowadays coming with so intelligent, right? A lot of intelligence. Once when we are plugging this to the grid, if there is one more charge, when you are coming in the grid, you are trying to connect with the grid. Now, you no need to tell that it is a like single phase grid or three phase grid or DC grid or three phase grid is kind of form. These chargers are so intelligent. They are taking information to communication channel. Like they will change the voltage. Like and based upon that, they will understand. Right, it is a single phase grid and based upon the style of the grid. Means based upon the voltage that is AC and DC and the voltage value and the frequency value. It is now initiate. It is reconfigured. Inside the power controller will be there. The controller will be there. They are switching, means they are reconfiguring them based upon the connector. Like that, they are doing it. So And here also in the connectors also they are making universal type of for DC we have different types of connectors. For AC we have different styles in different Japan, US, Europe, different types of connectors we are having. But now they are working on it to make a universal type of connector charge connector. Right. So level 2 and level 3. Uh, what we want in case of level 2 and level 3, we wanted to increase the power handling capability such a way that it can charge very fast. Right. In case of level of 1, we have a very low power, but you can charge very low power rating vehicle like 2 wheelers and all. But if you wanted to charge it very well, you need to have level 2 or level 3 so that you can charge your vehicle in sufficient. Right. So and level 2 and level 3 can increase distribution losses because you are taking a lot of power and also with a lot of harmonic components. In that case, every component of harmonic is contributing something like the losses, right? And also voltage will be there, and BGM and memory can increase by level 2, level 3, and thermal loading on the distribution system also. So we need to handle these things. Uh, just upon our um, so we need to have a reliable and efficient technology to handle the above set. We'll see that how much efficiently we are extracting the power and we are able to charge the our vehicle in the assembly. Right, with different motors also have done it. At least one charging or two will see it. Right. So different organizations, different societies, and different countries, and those things that happen. If someone is working on chargers, they can refer different standards are available, and we need to meet it. We need to go through it. Right? So, yes, this is about automatic engineers. This standard will say that command to command. This is for natural computer. This standard is for computer. This is related to power. This is related to other stuff. Where you are working accordingly, you need to go and deep and you need to check the requirements and you need to fulfill it like that. So, right, this is like uh, Germany, right, like that, different companies, Japan. Right, so this is for IEEE and this is of IEEE, this is of National Fiber Consortium. We have different standards depending upon which season you are there and which country. Accordingly, the country there is some kind of standards which you need to fulfill. Then only you are allowed. Right. So, all right. So these are about the standards and um, different standards and different now I wanted to give more focus to the charging, the design and development on the handle. So let me go ahead. So these are the various. Since we already time is perfect, so let me go on to the simulation of a charger and then let me come here on the different power converter for this available for the charging to meet the requirements of the different businesses. See that how we have developed this charger. So this is my solar, like I have taken, this is like modeling of the solar, like I taken like 10 to 50, there is a model, this is like 250 watts, smart 250, 250 watts module, and I have taken, let me show you that. So this is like module data, PV module data, which I have like standard. This is like module when you buy the module, or you will get the data from the your manufacturer. So you need to keep it down here. Directly you can depend. I have taken 14 such modules in series, and then 3 such arrangements I have taken in parallel, so that I will get uh, required power. Right. So you see that like 42 into how much 14 into 3 42 into 250. This is like 10.5 kilowatt solar PV module, and this is my battery, vehicle battery. Uh, so and this is my gate. You can see this is my gate, and this is my bridgeless perfect correction command. Right. So these are my inductor, boost conductors. So bridgeless topology. We are not using any additional diet bridge or something like that. We are getting all the ACPCMs you have seen single steps. Alright, so and we have a battery here, and this is the battery DC converter. So now the main role is comes here into this control. You see that this is our MPPT. If we wanted to extract the 10.5 kilowatt power from the module, because like you see that I kept initially at point 2 I changed my relation 1000 to 600, you can notice here. Right. So it is at 0 to point 2 my relation is 1000, and at point 2 my relation is 600, right? It is at point 2. Accordingly, you see that. You see the result. Uh, uh, I'm going to go to plot on the graphs. You can see that. Else I can show you the Alright, first let me show my PV stuff. So you see that at point initially it is external power of 10.5 kilowatt. Like you can see that. And at point 2 I decreased my radiation, that's why my PV power is decreased. Alright, it is now like 5800. Since I have decreased my radiation, accordingly my current goes down. Alright, so this is my voltage profile, this is my current of my PV module, and this is my this is what the theory says, and accordingly my results also. Alright, so what happens to the load? That means profile. This is my battery association, this is my and power. This is my capacitor, this is my voltage, this is my power. Alright, so and the same thing which I have plotted here from here also. So you can see that as shown, and like initially you see that this is like initially this thing is at point 2, this thing goes down because we have like that. That one is the capacitor current. If you want, we can see the PV voltage current and power. These are the power voltage, current, and power. Which I plotted there. This is like average values of that. And so now what I wanted to show you is that first of all it should operate at unity power factor, and it should have very good quality of the current from the grid. This is the grid parameter you see. See, this is like my grid current. This is my grid voltage is up one and down one is my grid current. See that it is having very good quality of current. It doesn't have much harmonics. You know, it is almost like science or stuff. Right? What we do is like that you can see. This is my at 0 to 0.5. So this P load profile is P. I'm changing my load. Means I'm changing my uh, charging at different powers. Initially it is like point minus 1 and after that it is like point 5. What is this minus 1 and point? It is in per unit. I have taken complete power is 30 kilowatt system. I have this from you here. This is like PDC is like 30 kilowatt, right? So initially 30 and then it is 50. So accordingly, what happens is that whatever power you are having, here you are having 10.5 and 30, then the net is going here, right? So that is what happening here. You see that at 0.5, right? 0.35 I'm changing, right? At 0.35 I'm changing. That means that. So you see that the battery parameters gets very important. See that initially this is like for see because your current charging current is changing. So like you see 3.2 since my radiation is 1,000, so it is charging at minus. We see the power. I think you understand. See, we have set here how much minus 2 point minus is like 25 kilowatt. You are having battery. This is like battery parameters. You see what I want to show you. This is the battery input side. This is coming from the battery input side, and this is like battery output side. I am measuring like I battery one. This is the battery output side. This is the input current and output current and associated. So you see, it is going from charging to discharging because you can also see that according to SOC is also getting changed. Uh, you can also see the power balancing it. Power balancing also you need to justify whatever you got it. Okay, you see that. Uh, this is my solar and this is my. If you sum these two, this will has to come. Right? This is about like these two. This will change negative means charging and this is discharging. Right. So you see that if you take a minus of this minus or minus this will be equal to this. This is the power balance. You see all the time it matches the power balance. So this is all happening. So how it is happening, we will see. I will discuss about the this proper power management when you are having a more sources you need to take care. So what happens first we need to take care. I apply to the PV power, whatever available power from the PV, we need to take it. And once you are having that, the net power you want at which you wanted to charge. Let's say I want 10 kilowatt I have and I wanted to charge that let us say 25. So remaining 15 should come from the grid because you have decided that you wanted to charge it at 25. So remaining power has to come from the grid. That is what we need to do. So first is the MPPT will tell that this much power is available, and second information we need to get from the load. That actually to maintain my DC bus I am trying to maintain at 790 volt. To maintain that it is like a loop control. It will tell to maintain at this much available solar power and this much if the load is there to maintain that how much current is required that is can be calculated with the help of this loop current loop control. will tell, you see that this is to control the VDC and trying to maintain 720 that will decide, that will control my battery side converter. And this is the control strategy for the charger. Right? So what we need to do first of all at point of common coupling we need to sense the voltage and from that we need to calculate the frequency phase angle and omega t and then we need to convert into VD and DQ and we are applying DQ control strategy that is more better than actual control. So right. And we need that based upon our current reference power this is like ID and IQ because I wanted to get a unity power factor. We can also see that it is operating at unity power factor. By seeing the current we can understand. See that this so this actually we have measured current in opposite direction because it is we are at a negative current initially. So it is like positive means the current should be negative. Exactly. Right, you see that. That is what happens. In discharging, you see that this is positive and this is also positive. You can see that both are like coinciding each other. You see that. This blue is here peak and your current is also here peak. So uh, this is how we are able to maintain the quality of power in the current of the sinusoidal. Typically, you will not get it like this if you are not applying proper control. So currents no longer use sinusoidal like this. Right. So you are achieving unity power factor and good quality of power. If you want, you can see here. Uh, this is the quality of so this is the how much quality of powers. This is like almost same sort of right. So and even you can measure THC also. You want to go ahead, double click on that and go to FFT analysis. And then you can see the parameter TH1. What is the name of the parameter? And no, this is so scope data 29. Scope data 29 and we have this is my current. Uh, and, analyze that point 2, right? So, see that the quality of power is like 2.69, it's less than 5%. What actually we need. Less than 0.5 we need to achieve, so we achieved it, and that is the beauty of our design. This is what we have seen here, right? So this is the waveform that we have analyzed the quality of the current which we have. So like that you can we have achieved unity perfect and we are achieving 2 point something perfect this harmony this mean it should be less than 5. We are at 2.6 we achieve. And also if you want you can see the list. Uh, See that the DC offset current this is one of the requirement. We are only 0.2 on the person. There you go. So at different frequency components of they are. None of the harmonic is greater than 3%. Even like one requirement is that total harmonic distance should be less than 5%. An individual component of lower order should not be exceed more than this. These two are the one of the requirements of the standards. So for none of that you is more than even 1.1. So that is predefined. So these are how you should design it. That is how you should control. Like this you can make, and like that I have done it for different types of converters like A7 and HI. Like that I have even I made complete solid state transformer also. Solid state transform is that these are all for like different functionalities like SSD. So you have had SSD is like solid state transform. Anyway, SSD is not our job of discussion now, and now time is over. So like this we can so like this you can make a lot of simulations related to VMs or DC microwave and each of the solar power use of the DC microwave use of you can make different kind of things what you learn. So you should try to whatever you learn it try to simulate it so that your understanding complete understanding of the particular system will be increased. Once you have done that, then you try to go for the hardware development like that. And you have any questions, feel free to ask. And, maybe you can also ask later whenever you are facing issues where you are so with this, to start my discussion. Uh,
Thank you, sir. So with that, we will conclude the today's proceedings. So we will meet again tomorrow morning at 9:30. Tomorrow's sessions will be by Dr. Vikli Suresh sir from NIT Goa. So thank you for your patient listening.
Thank you very much, sir, for organizing such a wonderful event. And, thank you very much for making me part in our activities.
Thank you, sir.
And thank you very much for the whole department of electrical and whole management of this Vignan and Atal for sanctioning this activity to Satish sir. And thank you very much.
Thank you, sir. Thank you for participating in this event and sparing your valuable time.
Thanks, and thank you very much, participants, for spending your valuable time to listen